is touch, right?
Yeah.
We accept. Can we do that? Because
Yeah.
yeah. Okay. Okay. Okay.
Oh, yeah. Oh, that's not bad. Sorry.
那时候是我，是我。
May I begin? Honorable judges, fellow physics debaters, and esteemed guests. This is a reporter from GGWP reporting the topic 14 water bottle rocket. So this is a problem statement. Pump air into a plastic water bottle, partially filled with water, and under certain conditions it flies into the air. And we're going to investigate the acceleration during the liftoff phase. And these are our focuses: the theoretical acceleration, where we're going to compare it to our experiments, which are the variables, focusing on water amount, pressure, fins, and extra weight. Let's start with phenomenon first. This is a video of us doing the experiment, and this is our model. So we can do, let's start from the top. The top is a nose cone, and throughout the entire experiment, nose cone stays on the water bottle rocket. And these are the relevant parameters, and we're going to get into it in the later power slides. So let's start with the observation and the assumptions. So the first observation we see is, after doing a lot of test runs, the rocket tumbles before reaching the maximum height. This forces us to consider only the liftoff of the rocket launch, which is also correlates to the problem statement. And the next one is, throughout all of our experiments, we shoot the rocket 90 degrees vertically from the ground up into the air. And we consider thin-walled rocket body, which also means we're neglecting the thickness of the water bottle. And the last one is, we define the whole experiment into pseudo 1D motion by saying the x-axis cannot change from the y-axis 2 centimeters from left and right. So this is our theory introduction. Let's start with conservation of momentum. So from the conservation of momentum, we can get the F of t, which also means thrust force. And when a water bottle rocket fires, thrust is generated from the expelling water or later air at a high velocity through the rocket's nozzle. So you can think about it as this: air is pumped into the water bottle rocket, and then the nozzle is, when the nozzle starts to escape, water gets pushed down, and then generates a downward velocity for the water exiting. And then, according to Newton's third law, generates an upward velocity, forcing the water bottle rocket to go upwards. And this is the formula for thrust, as I stated. And the next, we consider it an adiabatic expansion, since the air volume expands very quickly when water exits. This also means we're neglecting heat loss or heat gain during the entire internal of the water bottle rocket. So this is the adiabatic expansion formula. We also apply Bernoulli's equation. And the reason we can apply Bernoulli's equation is from observation. Through countless test runs, water exits the water bottle as water columns, meaning Bernoulli's equation applies. And these are parameters we're going to be neglecting. So the first one is flow velocity at air and water interface inside the rocket body is negligible compared to U, which is the exiting velocity of water. Due to the rocket's elevation difference as it flows from inside to outside the rocket, the change in gravitational potential energy of the water is negligible. The last one is the water flows under quasi-steady conditions, which can conclude that fluid friction are negligible. The next equations are mass flow rate combined with thrust. So combining these equations and then substituting thrust into Bernoulli's equation, we get equation number 6. And combining equation 2 and 3, then we get equation number 7. And after, we differentiate it for u in the function of time. So we want to express u in the function of time for us to create a theoretical model. And next is the rate of change of air volume inside the rocket body. It's also equal to the volume flow rate, expressed in AU. After combining equation 9 and 8, we get equation 10. And then substituting v from equation 10, we get equation 11. Equation 11 is basically the overall formula for u in the function of time. By integrating the u in the function of time, we can solve u throughout the entire experimental setup. And in order to calculate u at time equals 0, we can solve u by using Bernoulli's equation, and then further putting it into the equation with the thrust in order to calculate acceleration, which is our ultimate goal. Next, I'm going to introduce Reynolds number. And throughout the entire experiment, Reynolds number for air is more than 1,000. And the reason we need to thoroughly discuss Reynolds number is because in order to apply drag force, Reynolds number must be above 1,000. After applying source force into equation 12 and 13, we get acceleration from dv divided by dt. So let's start with the preliminary experiment, drag coefficient. From the drag force formula stated here, we need to calculate the drag coefficient. To measure the drag coefficient, we drop our water bottle rocket to reach terminal velocity. And to do this, we calculate water bottles without fins and with fins, and the data are shown here. And to ensure the most stable launch, we reamed the commercially sold nozzle to neglect friction and not to minimize friction and optimize the motion. We do this by drilling the internal, as you can see from here, the internal surfaces are not really flattened, so we want to smoothen it. So we use drills to smoothen the surface area. And this is our experimental setup. We have the electrical pumper here, and then the launcher, which is a commercially sold launcher. And then this is our bottle rocket, which has 485 milliliters volume. And one of the experiments variable is extra weight, and we add it on top of the bottle, inside of the nose cone, and tape and clay and apply tapes around it in order to force it with the water bottle rocket. And we use throughout the experiment, we use high-speed camera, which performs at 960 FPS per second to record our entire experiment. So the boundary conditions are, in order to launch a rocket, which, as I mentioned, is 485 milliliters, the minimum amount of water required is 55 milliliters, and the air pressure is 30 psi. So the first experiment, we're going to discuss pressure versus water ratio. We're going to change the water amount, also known as the water ratio, and increase by 50 milliliters. So as water decreases, acceleration decreases at time interval. And as we add more water into it, the acceleration decreases. This is the experimental data, and this is the theoretical data. Okay, so this is also applies with 70 psi, and a constant at 70 psi. You notice that as we add more water, the acceleration decreases, which conforms to our theoretical model. And next one we're going to talk about is water ratio versus pressure. So we're going to change the pressure from 30 psi to 70 psi with an increment of 10 psi to launch our rocket. So we make our water constant at 100 milliliters, and as we pump more pressure, the acceleration increases, shown in the both experimental graph and theoretical graph. This is also shown in constant 300 milliliters. So the third experiment is fins effect. We're going to investigate the effect on fins on the acceleration of water bottle rocket. We're going to do this by having fins or without fins. We're going to stabilize the water to 100 milliliters and 300 milliliters, and the pressure is stabilized at 30 psi and 70 psi. As you can see, there's not really a big change in the lift-off phase for the acceleration for fins and without fins. And this is because drag force is affected at a minimum rate as there's minimum amount of velocity that as the rocket first launches into the air. And if there's any sideway motion, then the air is striking, the fins pushes the rocket back towards straight motion. This is also used to stabilize the entire trajectory of the water block to launch. And the last experiment we set up is adding extra weight. And we add weight, as I've shown in my experimental setup, from 0 grams, from not adding anything to a 50 grams weight to see the difference between for the acceleration. As we add more weight, in this case 50 grams, the acceleration decreases. And you might notice a trend of the different slopes for these, and we're going to explain on that in a few slides. So extra weight reduced, after doing it for the 300 milliliters, we noticed that it crosses a meeting point. Because air resistance affects heavier rocket less, the acceleration of a lighter rocket decreases more quickly. As for the conclusion, the higher water to air ratio, the acceleration decreases. And as we pump more pressure into it, the acceleration also decreases. And we add fins to the rocket body. It will not affect the acceleration during the liftoff phase, but we conclude that it will stabilize the rocket for the entire duration of the flight. And the last point, while adding extra weight reduces the initial acceleration of a water bottle rocket, the heavier rocket's increased mass makes it less affected by drag, causing the lighter rocket's acceleration to diminish more rapidly until their net acceleration may converge. As for future research, we wanted to, as if we have more time for the experiments, we want to optimize the launch of the water bottle rocket in order for it to launch it vertically, because as I mentioned in our observation and assumption, it actually tumbles even before reaching the maximum height that it's capable of. And the first step of doing this is we can rebuild the existing water bottle rocket launcher using other materials. Because as I stated in my experimental setup, we use a commercially sold water bottle launcher and want to make our own with, for example, pipes. And want to find the optimal weight for the water bottle rocket in order for it to launch the highest. And this is our reference, and this is the end of my presentation. Thank you.
Go ahead.
I have a question. You mentioned that the adding the fin stabilized the trajectory of the rocket. Can you show the data for that?
Pardon?
You said that adding the fin stabilizes the rocket. Can you show the data?
No, this is an observation that we've noticed from shooting them multiple times using fins and without fins.
Oh, so that's enough. Okay. Have you considered the effect of any compressed gas in the bottle that's left over after all the water has been launched out?
We define lift. Okay. Let me. So throughout our experiments we conducted, the acceleration we view is from 0 to around 0.1 seconds. This is what we determine as liftoff phase. Okay, so your question is about how compressed air after the rocket.
I'm saying that if the bottle launches up and then runs out of water, there can still be some gas inside that's still compressed. Do you think that will happen?
Okay, so we define liftoff as before the okay.
So you just decided to not include it in your liftoff?
Yeah, because it's not part of the liftoff phase as our definition states.
Okay.
Okay.
Could you guarantee that the rate of gas inside the bottle is the rate that the volume of the gas involved is expanding proportionally to the rate of the rate that the volume of water is leaving the bottle?
Do you mind restating?
Okay, I can explain this more later. Have you also considered calculating the Reynolds number on the exhaust flow out of the bottle?
It's. What do you mean? Why should I calculate the Reynolds number?
Just convenient with converting the turbulence to laminar.
We can discuss it later.
And I'll be including the water, topic 14 water bottle rocket. This is the pump statement. And pump air into the glass water bottle to measure the water. Under certain conditions, the bottle is launched in air. Investigate how the acceleration during the thaw depends on relative parameters. I believe that the more ideal model to further investigation is first trying to predict the thrust and also measure trying to predict the thrust and also find a way to measure both the force and mass of the rocket to be the two variable measures the acceleration. First, there also needs to be an investigation of certain properties of the flow and also given time will be explorations up on the effective drag of the water. This is my opponent's structure of their research. They first developed a theoretical model for the thrust and the acceleration. They clearly provide their equations and also their assumptions. They conducted their experiments on both the drag coefficient and thrust by doing full-on experiments. And they vary the set of parameters and compare the results from each of them, such as the volume to water ratio in this model and the effect of fins and the fins on the rockets. I think that the opponent had a really good controlled experimental setup. Each of their conclusions were clear and on what they believe how the parameters are changed. And their presentation was well organized with clear points. However, there are some unclear parts and observations that I need to clear up. And not really elaborate on how they were collecting their data how they were collecting their data. They were only explaining how they conducted their experiments. They also did not address air expansion, which I still believe to be significant. And there's some missing parameters and there could have been some more data to support the argument rather than just observational data. And there is also the error analysis during their presentation. These are the three topics I want to focus on. First, I want to look at their experimental data and possible sources of error. I want to look at some certain characteristics of the exhaust flow that the opponent may have failed to address. And I want to look at their conclusions with parameters and discuss the reasons behind these conclusions. So first of all, I want to talk about how you collect your data.
For the experimentals?
Yes.
Yeah,
but how did you obtain those results?
You mean the left or the right?
Both.
Okay, let's start from the left. The experimental data, as I stated, we use 960 FPS high-speed camera and we put it into tracker in. We only plug in the data for the y-axis, so then.
So they could be potentially be some deviation as trajectory that you do not.
As I stated, it's a pseudo 1D motion, and the x-axis is within 2 centimeters.
So you think you ensure that it's straight enough?
Yes,
Okay.
that's
Let's elaborate on the graph on the right.
okay. So this one, okay. Let's go back to my theoretical data. So this is my integration for solving exit velocity u, and I put it into a coding system, and then to solve u in the function of time, and so.
So that was already a theoretical curve.
Yeah.
Okay. Do you account for any errors like that?
So our data from our experiments are, we have actually averaged it, and we did include an error bars.
Oh, wow. So they could have an error.
Yeah, they could. We didn't add error.
That should be okay. Do you also how the same case? Do you have any sorts of error with your drag experiment?
Drag experiment?
Yeah, like how certain are you on your calculation?
For the coefficient, drag coefficient?
Yeah, drag.
Are you saying when I dropped it, it's going to be wind flows and other stuff?
How certain? Are there any other?
So we actually done many times. We actually do it many times, and we track it. We track it to make sure it's entering terminal velocity, and we're applying to it the drag coefficient, and we can calculate the drag.
So you're just confident that you.
Yeah.
You're confident.
As you can see, we actually done it in a semi-open area. So there's like, and we minimize. We did the experiments in minimum wind effects.
Then I have something else to address. Since the drag coefficient requires is calculates it relies on the area that the air flow is pushing against the rocket, but you also think the rocket is tumbling throughout its trajectory. Wouldn't that affect this?
You mean the drag coefficient may
Yeah,
be?
would that affect the drag force? Even if deviate just a little bit, wouldn't that be changing the area?
As I stated before, the liftoff phase, we wanted it to be y-axis upwards. So we didn't account for any tumblings. We didn't include the data for tumbling because it's after the liftoff.
Okay. So the primary reason that you did not address so many things on error is just that you seem to be confident that you have connected enough products with you.
Yes.
Okay. Then I think in that case we can move on to discussing some other parts of our theory.
Okay.
First of all, can you go to your equations with us?
Up here?
Previous, when you were driving like the adiabatic equation, the adiabatic. Yeah, from here.
Oh,
I'm
here.
wondering what the C stands for.
Oh, the C is the adiabatic expansion constant in page for the
From my understanding,
yeah.
it's constant.
Yeah, it's a constant.
Yeah, I understand constant, but what do you define as constant as?
So we plug in the initial P0, which is initial absolute pressure, and V0.
Oh, so you're just solving it as P naught V naught.
Yeah.
P naught V naught K. Okay. Earlier during our discussion, I mentioned that for the theory to be correct, you need to assume that the volume of gas in the bottle is expanding at the same rate that the volume of water is leaving. Meaning, however much water is leaving the bottle, that's how much the air in the bottle is expanding. Do you assume this to be perfectly true? Because this must be true in order for the theory to be correct.
Yeah, I assume it's true. But for the acceleration, for calculating the acceleration, we did not. Our main focus was on the exiting velocity of the water, which is we plug it into the
Yes, but
U squared. Yeah.
you're relying on the expansion of the gas inside the bottle, right?
Yeah.
That's what adiabatic
Yeah.
is. But then, so you just have to give a guarantee that this is the case.
Yeah.
Okay. Can you confirm that when the bottle is towards the end of its liftoff, did the exhaust ever become less adiabatic? Not adiabatic, not laminar. Did it become less laminar?
Less laminar.
I would say that I would describe it as kind of like burst. Like there was like the air is getting mixed with the water.
Let's go to this slide. Okay, so the water flows under quasi-steady conditions, and the reason we're able to predict, to assume that is because it conforms to the Bernoulli law. And in order for the Bernoulli law to be appropriate, it needs to be quasi-steady conditions. And our experimental data conforms to the Bernoulli equation, so that's why we assume it's quasi-steady flow.
So you're claiming that the reason why it has to fall laminar is that your experimental model didn't match up.
Yeah, it matches up.
Could you show it?
I'll give an example.
I was thinking like because you provide so few error bars. I'm not very confident in how well your data is lining up with the simulation. Like
You can see the trend.
you're only confirming the general trend. I don't see the actual comparison of the values. Do you think is that even worthwhile to compare?
It's obviously worthwhile to compare, but from the trend, we can confidently say that it conforms to the theoretical.
I think you should still compare the value. For example, what if, because just judging from the scale of the graph is a little wide. Like, why do I think that the top line is decreasing at a faster rate than predicted? What if that's an actual pattern inside the data that you're not accounting for?
Do you want me to derive the data?
So what I'm hoping is that due to the fact that you didn't give a lot of actual analysis of the error between your data and your predicted, I don't think you can really give much validation to your theory. Because
as I stated, we've averaged out all of their data together into this chart. So
but at
we
least
can
compare
confidently.
two graphs besides just this trend. At least like line it up on the same graph. I want to see if it's lined right in the exact same value. Rather,
You can see from the left the acceleration, and it's
sorry,
pretty much matches up. Okay, we can take a look. The scales are pretty much the same.
Okay. Another form I wanted to talk about earlier during our discussion was with the Reynolds number on the thought.
Okay, for Reynolds numbers,
I understand your use of the Reynolds number on drag. I was
Yeah.
want to talk about the Reynolds number on the thought.
it's inside of the water bottle.
It's shooting it. that using the velocity?
Estimate that using the velocity.
Yes.
We did not account for the Reynolds number inside the rocket because we can assume it's quasi-steady flow.
Could you at least guarantee it by doing calculation? Could you at least give a calculation to assume that it's under 200?
We did not do a calculation for Reynolds number inside of the rocket.
Okay, then could you give like a general number on how fast the exhaust flow is usually?
Exhaust flows, okay, I can just show you the chart. Actually didn't put the chart for the velocity. So it's around, for the starting point, it's around 30, and then it decreases to like 20, a little bit over 20. For the velocity, you mean this is for the exiting velocity, and for the velocity of the entire rocket, it stands from around 0 to about 10 or 20.
Well, it's that multiplied by the density of water, which is a little high in standard unit, multiplied by the length of your nozzle, and divided by a relatively small cross-section area. Could you say that the Reynolds number could potentially be pretty high?
Yeah, the Reynolds number could potentially be really high.
Then would that mean it's more closer to a turbulent model than a laminar model?
As I stated, our assumption is that it's a quasi-steady flow, and we're clearly
But if that's
proven that it's.
well, if that's the case, could you give an explanation to why the Reynolds number is so high? Could potentially be so high.
Potentially there's a lot of outside factors that could affect the Reynolds number, so I would say,
I think it's a pretty fundamental thing that you want to confirm.
yes, it's maybe something I should actually put into the data.
Let's move on to my final topic. Let's look at your conclusions. Let's go to the conclusion slide.
For the
The entirety, because I want to look at your conclusions on how the parameters would change. Because the part that I felt was a little strange was, the part that I felt was strange was that you claim that when you build up more pressure inside the bottle, that causes the acceleration to decrease. Have you plugged that into the simulation? Your set of equations and make sure. We can go back to the set of equations.
Set up equation.
Yeah, your equations. Like if you actually plug like an initial value into there.
So it's done in the second experiment. As we raise the PSI, which is the pressure amount, the acceleration decreases. I'm sorry, that must be a typo. The acceleration increases.
I see. That's pretty.
Yeah.
Sorry. Let's go back to the conclusion slides.
Okay.
I'm sorry. So it's just a teacher to look at all your conclusions. So you claim that there's an importance between the water to air ratio. I just want to question, this is only about the initial?
Yeah, that's the initial.
Okay, could you, what do you think, what would happen if you were comparing pressure? Water to air, good water to pressure ratio.
If the water, okay, let's look at it.
Actually, it's okay, we don't have to.
Okay, I noticed you mentioned about the deviation. Do you have any questions about that?
Deviation?
Yeah.
I was thinking because like, if you want to convince me that these the values are exactly from each other, like there should be some statistical analysis, because I don't think just lining two graphs next to each other is not sufficient, and just claiming the trends. I don't think that's very sufficient, especially since you already see a lot of variation within the
But
data.
obviously there's going to be a lot of variations because shooting the rock in water bottle.
Well, yeah, but I think there should be some analysis.
Time's up.
So we had a discussion on the experimental data and the discussion of how the reporter collected their data and how they were analyzing the error. While the reporter is relatively confident in their results, I still think that some statistical analysis is required in order to confirm that the data actually lines up with their simulation. And we also discussed the characteristics of the exhaust flow, while we focused on the potential of the flow being turbulent due to Reynolds number, the supporter came out being enthusiastic. Okay, go ahead. Reviewer.
So now, first I want to ask for the report. How long is the duration in your experiment? You measured. How long is the duration of the experiment?
0.1 and then.
So is that the lift-off phase? You define
We
that.
define the stop phase as when the water not.
Add the water. Okay.
Yes.
Okay. Next, I want to ask the opponent. You said you asked for the report when the velocity, when the volume of the air expands. That you think? I'm assuming that you don't think that is related to the water.
I think under certain conditions, yes, but I think when there are situations where,
So depends on this.
I think there are certain situations where, under conditions, there could be the situation where air starts mixing with the exhaust. In that case,
Okay.
the
You
exhaust,
think that there's a mix? There might be.
I don't think
where
it will be
the air
more.
and the water mix
I
together.
don't think the exhaust is going down that much.
Okay. Then okay. You mentioned that the velocity you measured from the exhaust water speed is around 30 to 20. Is that correct?
That's
You
correct.
mentioned, and is that to ground speed or to
It's relative velocity
relative to where to what
to the upper velocity
of the
rock.
rocket? Okay. Then I want to ask report again about the turbulence because in your I think it's the pressure graph. There's some turbulence. The
Wall.
yes, the wall effect. Could you explain more about what causes that turbulence?
Doing the water bar experiment requires doing outside, and then there's obviously a lot of outside parameters that's going to affect the phase.
For example,
For example, wind velocity and
wind velocity,
yes, it's going to affect.
pressure in wind
No,
velocity.
the outside, right? Because we're doing it outside. Right? Shoot a lot of.
So you can counter
Yeah, outside.
environment.
Yeah, environment.
Environment parameters. What do you think, opponent?
Sorry.
Okay, okay. Next question. So do you think when the water is pumped out completely, do you think even though if the water is pumped out completely, do you think that there's still be acceleration due to thrust?
I think, yeah, there would be, I think, much smaller than one water fire to be
Okay.
able
What
to
do you think?
Yes.
Yes, there's still.
Yes.
So that's okay. Now, do you think that the Bernoulli's law can be applied in the whole process of your experiment?
Yes.
Yes. What do you think?
no, under certain
No.
conditions.
Okay. So, do you think there's a optimized pressure or optimized pressure and water mass that's going to be that's going to cause the rocket to have the largest acceleration?
There's the top phase.
Yes.
Yes.
There's the topics. Yes. What do you think?
Pressure, no, water, yes.
So only water.
I think water is the most significant, and added mass.
So,
But
so by changing the water mass, you think there's going to be an optimized.
Yes, because
acceleration? Okay. Thank you. That's another question. I'm the reviewer of this problem, and so the pros and cons on the observation for the reporter. The first is they have a clear observation about the rocket acceleration through. And they say that the rocket is ejected in vertical direction. As they say that they use it's one direction, and the deviation is around is within 2 centimeters. And for the theory, it uses Bernoulli's equation to describe the motion of the water being pumped out. And for cons, I don't think they have a clear physics idea on that equation. As for the experiment, they measure the air drag force and the pressure inside the rocket, and then they do the experiment about the fin effects, and they added extra mass. For pros, they've done several variables, but however, I don't have clear mechanisms about, like for example, how they release the pressure gauge, or like how they added mass, such as the other clear mechanism about how they actually establish that. And for analysis, they again have different variables that change the acceleration. And the pros is they have a clear figure about that. And for the opponent, they have the presentation. They have clear sides, and they have a quick and short questions. I think that's important. And about the discussions, the opponent didn't think. The opponent said that they didn't understand the way to connect the data, and the report said they use a 1D motion thing, and so the camera use the camera to track the motion and describe the motion. And the opponent asked, what's the drag coefficient? What is the drag coefficient? How does the report measures the drag coefficient? And the report said they use by calculating and examine the terminal velocity. And the opponent asked, why is there no arrows? And the report said, I've done it with confidence. And for the time duration of the liftoff phase, because the report says the duration they observe is the liftoff phase, which means in their definition, the liftoff is caused when there's no water pumped out. However, even though when the water is pumped out, there still have acceleration due to the differences pressure in air inside. So therefore, I think the definition in the liftoff phase isn't clear. And yes. And I asked what's the velocity of 20 to 30? It says to rocket. And I think that yes, the velocity on that should be relevant to the rocket. And for the turbulence, of course, it's due to outside pressure. And in my opinion, I think it's because the water isn't a steady flow. That's why that causes the turbulence in pressure difference. As for the appliance of Bernoulli's law, I agree with the opponent that you cannot use Bernoulli's law because that's not a laminar flow and there's turbulence in the water pumped out. And for the pressure optimized, I think that the opponent saying yes, it's water, and of course I guess it's a bit to that.
For the concluding remarks, the opponent discussing with me about I should add more error bars and line the data up with my theoretical data and my experimental data to ensure that I have the most precise trend and to make sure that the trend actually aligns with theoretical data. And I believe that's a really great suggestion that I should implement in future researches. And the second one is for the liftoff phase. I define it as when all the water has exited. And for the third one, the opponent suggested that I should include Reynolds number, and it should be considered inside the water rocket for it to precisely say that it's a quasi-steady flow. And the fourth one is Bernoulli equation. We firmly believe that we can use Bernoulli equation because it can be supported with experimental data. And as I stated, when we observe the water bottle rocket through a high-speed camera, the water exiting is at a water column, meaning it confronts the Bernoulli equation. And fifth, pressure can be put into a rocket with the commercially sold launcher. So the reviewer asked how we apply pressure into the water bottle rocket. So there's a graph of an experimental setup. I actually push the nozzle, there's a mechanism inside the launcher, and for it to force the air inside and releasing the nozzle, making it fly into the air. And maybe I should have clarified on that a bit more in my experimental setup clarification. And for the last part, overall, we should have added more error bars to fit in our entire theoretical and experimental data, and we should have accounted for a few more parameters when conducting this experiment. That's all. Thank you.
Question from the jury.
Okay, then I have a question to all three of you that in reporter's experiment, they assume the drag force is proportional to square velocity. However, the drag force is really complicated in physics. And drag force can be proportional to velocity or square velocity or a combination of them or more complicated form. So do you think whether it makes sense to assume the drag force is proportional to square velocity? Reporter, please.
Yeah, obviously we assume it's applicable. So we actually discussed with our physics teacher before we even conducted the experiments, and we talked about it, and this has actually like minimum effect. So we consider it as both applicable. So however we apply U squared, yes.
Okay.
And I don't think it's directly V squared because at low speed there's two terms on there should be two terms on the drag force. One is one is AV plus BV squared. So that's two terms.
Okay.
So I heard of the V, so it's like primarily limited V squared relationship, but I think to do the absolute velocity, it can be somewhere in between. And you can jump into determinant of the Reynolds number.
Okay.
So for the reviewer, so this problem is to investigate how the acceleration during liftoff. So how do you define liftoff?
Okay, so I think the lift-off phase of the rocket should be when the acceleration of the thrust is equal to zero, not when the waters completely come down. Because the difference between this and the reported definition is because even though when the water has been come out completely, there could be pressure differences inside the rocket and outside the rocket. So in that exact moment, there should be a sudden pressure drop, and that drop causes the extra push of the rocket. So we have to consider that case as for the entire acceleration process.
I want to make sure in your chart, okay, because you have the different condition, is the liquid, right?
Pardon?
You have the different bar liquid in your bottle, right? But all of you record at the same time. So the acceleration before the arrive the maximum point, all the condition are the same or not? Because you just record, okay, all these condition, yeah, for the acceleration. Okay, understand. But I want to make sure all the condition, okay, they arrive the maximum point, in all the condition are the same.
For maximum acceleration,
Yeah.
conditions are the same. For the coding, we apply the same conditions. Yes.
So the time, maybe the equal, okay, it's just
Zero. Do you want to?
Okay, no, not the final time. Yeah.
Yes. That's
All of them in the same length, not
same length of.
height.
We launch from the same surface.
Means the height, reach the highest height.
Yeah.
Does the all the rocket reach the same height?
No, it doesn't reach the same height. Yeah.
I have a question. I have a question. Okay, since you have measured the velocity of the data and change the data into acceleration, right?
Yes.
Okay. Since you have the video tape, have you ever observed the bubble the water in the bottle, what's the action of the water in the bottle?
Water in, you mean,
In the bottle.
as it exits out?
Is it actually the up? Yeah. Have you observed?
Yes, we have. So as I stated in my
No.
earlier,
I mean the water, not the position of the bottle.
you mean
You mean, I mean is there the turbulence or anything, not the normal fluid, not the static fluid behavior? Have you observed?
I have, but
Okay,
what about it?
that's it. Okay. Jerry? Okay. Go ahead. For the reporter, 86678. For the opponent, 86678. Succeeds. For the reviewer,